In the previous lecture, I wanted to give you some useful formulas about trigonometric functions. These formulas may replace the analysis of a unit circle. If you, well, you can choose between the unit circle and these formulas, if you wish. To me, well, because I do remember these formulas for many years, and it's easy for me to use both, but I still think that a unit circle is easier. Here's the formulas. They represent trigonometric functions of a sum or difference of two angles in terms of the functions of those angles alone. Sine alpha plus beta and of course these formulas are more general than those for the unit circle. I will give you an example. You will see what I mean. Sine alpha times cos beta plus cos alpha sine beta. Okay. Sine alpha minus beta is sine alpha cos beta minus cos alpha sine beta. Look, these formulas are not part of this course, so you do not have to remember them. But in trigonometry there are many different formulas connecting different trigonometric functions. You just may keep these formulas on your A4 sheet for the exam if you wish, or just whenever you do your math courses or in the future at your work. You may just remember that these formulas exist and you may just have them written out somewhere, ready for you to borrow. Cos alpha plus beta is cos alpha cos beta minus sine alpha sine beta. And finally, cos alpha minus beta is cos alpha cos beta plus sine alpha sine beta. Now let's see how these formulas help us if we need, for example, sine 3 pi over 2 minus alpha. Let's use one of these formulas. If you don't want a unit circle, let's use one of those formulas. Which one? The second one. Actually, the second one. Yeah, okay, let's use the second one, because it's about the difference of the angles. Sine of the first angle, which is 3 pi over 2, times cos of the second angle, which is alpha, minus cos of the first angle, 3 pi over 2, times sine of the second angle, which is alpha. By the way, At this moment, why not use the unit circle, derive the answer from the unit circle, and then continue this formula to see whether or not we get the same answer. We need the same answer using whichever method. If I use the unit circle, I need to plot the angle, two angles. One is 3 pi over 2 minus alpha, and the second just alpha. Here's alpha. That's the point where we are. Where is 3 pi over 2 minus alpha? 3 pi over 2 is 3 times pi over 2. Pi over 2 is 90 degrees, the right angle, taken 3 times. 1, 2, 3. That's 3 pi over 2. And let's go back by the angle alpha. We subtract angle alpha. So this is alpha. We are here. What is sine of this angle? Where is the sine? Here's the sine. This length along the vertical is the sine of 3 pi over 2 minus alpha of this angle. What do we see from this picture? Well, from this picture we see that this length is equal to this length here. Right? Do you guys agree with me? Yeah? But this length, the horizontal, is nothing else but cosine alpha. Now let's check the signs. The cosine is positive. You see that this coordinate is positive. This length is positive. But this one is negative. Therefore, I must write the sign minus in front of cosine to make the signs right. Do you guys agree? Any questions? Now, if I use the formula, what do I have? What is sine 3 pi over 2? Look at these unit circles. Sine 3 pi over 2, what is it? I think that it's minus 1 from the unit circle. Because 3 pi over 2 takes us to this point. Minus 1. This is the sine 3 pi over 2. What is cosine 3 pi over 2? 0. Because if we are here, then the horizontal coordinate is 0. So what is the answer? Minus cos alpha. We get the same answer using both methods. One method, using the unit circle, makes us think. The other method, using one of those formulas, involves practically no thinking. If you have these formulas written out for you to use, feel free to use it. Now, finally, before we go to the next topic, how you memorize these formulas. When you have sine of a sum of a difference of two angles, then in the right hand side you have sine cos cos sine, sine cos cos sine. They alternate. The sign here between them is the same as the sign between alpha and beta on the left-hand side. Now, when you have cosine of a sum of or difference of two angles, then in your right-hand side you have cos, cos, sine, sine. Cos, cos, sine, sine. And the sign between the terms is opposite to the sign between alpha and beta. This is for you to use if you are enthusiastic enough and if you are hard enough on yourself to make yourself to memorize this formula. But if you are lazy, well, have them ready on piece of paper. Maybe useful. By the way, in the future, I do believe most of you will take further math courses. And you will need these formulas there in those courses. So you will need them. Okay, guys. Now I want to move to the next topic, which is vectors. You already noticed that I just run the lectures just through. I do not say the topic of today's lecture is such and such. In the end of this lecture, you will be able to do this and this and this and this. I'm not doing this. Every stuff like this is written in your study book. What I do, I just go through non-stop, but emphasizing the most important points. And also I'm giving something extra to the study book and the textbook. Very, very, very useful. The stuff which only I know. And I'm telling you, a secret. Very useful for you. Now, vectors. Vectors are everywhere around us. Intuitively, we understand what vectors mean. This is an object which has the length and direction. There are quantities which have no direction. For example, price. A price of anything has no direction, but has magnitude. If you consider velocity, then the velocity has not only the magnitude, but also the direction. How do we show the velocity? By a vector. A vector is displayed by an arrow. Naturally. Its length gives the magnitude, for example, the magnitude of the velocity, and the direction shows the direction. You may have your vectors in two-dimensional space, on a plane, or in three-dimensional space. And even in mathematics, you may have vectors in many-dimensional, multi-dimensional space. But let's just, for convenience, let's just talk about vectors on a plane or in 3D space. How do we denote the vectors? For example, u, let's call a vector u, and on top of it we draw an arrow. That's one way. There are different ways. In books, very frequently the vectors are shown in bold font, without an arrow on top, but the letter U will be in bold font, like this. this. Book. But when we write in our notebooks, of course we prefer vectors. Nobody would want to, especially if you write by hand, then writing in bold font would be inconvenient. We put arrows. Now, when we are in two-dimensional space on a plane, then it is useful to have a reference, some reference, or reference vectors. Here they are. Let's have usual axes, x and y. Which span a plane. And let's have a vector named I in the horizontal direction. I with arrow on top. With the length 1. And let's have the other vector j along the vertical direction with the length 1 as well. So the length of I, the length of any vector is shown like this, u modulus. This means the length of the vector u. The length of the vector I is 1, and the length of vector j is also 1. Why 1? Because we just choose them to have some simple length. Why do we need these vectors? Because any other vector can be represented as a sum of I and j with appropriate coefficients in front of them. Or I can say any vector can be decomposed into a combination of I and j. Okay. We'll talk about this later. We will see how do we represent an arbitrary vector as a sum of I and j. When I say sum, what do I mean? How do we add two vectors to each other? And one important thing I need to mention. When I say vector, usually I do not suppose that this vector starts at some particular point. It just hangs out in space. It is not attached to any specific point in space, unless this is specified additionally. Now, let's have two vectors, u and v. Okay, I have this vector u, which flies in space somewhere. And let's have another vector v. Each vector is not attached to any point in space, but each vector has its length and direction. They are specified unambiguously. When I draw an arrow, I immediately tell you what the direction is and what the length of the vector is. You understand this? Yeah? Now, how do we add u plus v, the two vectors? Here's how. Let me move a little bit. I will move a little bit this line. Okay, vector u. You draw your vector u. This is u. That's same vector u. At the end of the vector u here at this point, you attach the vector v. At this point, the vector v starts, and you draw your vector v. So the two vectors connect to each other like this. And then you connect the starting point of vector u and the end point of vector v like this. This will be u plus v. And this vector is the sum of the two vectors. Is it clear, guys? How do we subtract two vectors? Let's find the vector u minus v. Here's what you do. You draw vector u, let me move a little bit. Let me draw vector u here. Then at the end point of the vector u, you draw the vector which is opposite to v in direction and has the same length. It's the same as vector minus v. Look, u minus v is the same as u plus minus v. The rules are the same as for algebra. Vector v was looking like this, right? That was vector v. So vector minus v will go in the opposite direction to v, and it will have the same length. So I draw like this. This is minus v. It is parallel to v, goes in the opposite direction, and has the same length as v. And then you connect the starting point of the first vector and the end point of the second vector. This is u minus v. Is it clear, guys? Now, we can also multiply any vector by a number. Let's see what is vector k u, where k is a number. By the way, numbers or quantities which have only magnitude but no direction They are called scalars. Scalar. So, K is a scalar. U is naturally a vector. Well, let's consider a specific example. If K is 2, for example, then Ku is just 2U. 2U. The vector 2U has the same direction as U, but twice as long as U. So this was vector U, okay? Vector 2U will be twice as long and has the same direction. Now, what if K is negative? Can K be negative? Yes, it can. For example, it can be -1, like here. If K is -1, then Ku is minus U. It's the vector which is opposite in direction to vector U. It goes in opposite direction. It has the same length. Now, some rules. If you have your vector Ku, you can calculate its length like this. Just put vertical bars like this. They will denote the length of the vector Ku. Now, because K is a number, well, yeah, look, here's what you do. This is modulus of K times modulus of U, or the length of U. The modulus of K is a number. So this line simply says that the length of the vector Ku is equal to the length of the vector U times the absolute value of this number K. Simple. Now let's see how we represent any vector in terms of I and j. Those vectors, they are called base vectors. Let's sit on a plane. Let's have our usual axis y and x. And let's even have 0 here. But we don't need this. But I always like to draw this number 0 at the origin, because it brings a sense of comfort to me. In our room, we want to have chairs and TV and everything. Yeah. So, same here. Okay, where is vector I? Here's vector I. Where's vector j? Here's vector j. Now let's draw some arbitrary vector from the origin for convenience. U. Do you see that we can indeed represent U as a combination, namely linear combination of I and J? Some number k times I plus some number m times j. I can always find such numbers. Let's look at this picture. Let's drop a perpendicular from the end of vector u onto the horizontal axis. And let's draw this vector which starts at the origin and ends at this point. Let me have I and j in bold font. Okay, this vector will be u1. And let me put another vector from this point to this point. This vector will be u2. It's obvious from this picture that u equals u1 plus u2. True? So if you add the two vectors u1 and u2, then your resultant vector starts at the start point of the first vector and ends at the end point of the second vector. And the two vectors which we add together, they connect with each other like this. So u is clearly u1 plus u2, right, from this picture. Now, it is also obvious that u1 is proportional to I, because they have the same direction. And the difference between them is just some coefficient. So I can always write u1 as some coefficient k, a number, times I. Likewise, I can always represent u2 as some number m, which I need to select somehow, times j, because vector u has the same direction as vector j, but has different lengths. That's why we need to multiply j by some number m in order to get u2. Okay. So this is how any vector u is represented as a combination of the two base vectors, the basis vectors, I and j. If we are in three-dimensional space in which we live, then in addition to I and j, we also have the third dimension represented by the vector k. Let me show you three-dimensional space. X. I don't really need these notations x, y, and z because I do not use them. I just write them for convenience because we are used to having x, y, z. Vector I, a unit vector, goes along x. This is I. A unit vector j goes along axis y, and the third unit vector goes along axis z. This unit vector is called k. And any vector u of v in three-dimensional space can be represented as a linear combination of ij and k, like this. Ki plus mj. Well, no. I don't like this letter k repeated twice. So let me change the notation. Let me call the coefficients differently. PQR, P, Q, P and Q some numbers, plus R times K, a linear combination. What else do we need to know about vectors? We need to be able to find the length of a vector. For simplicity, let's sit on a plane. Look, I start my vector at the origin, but it's not necessary. Well, let me start it somewhere else. I just want to emphasize that our vector doesn't have to start at the origin. It is not attached to any point. Vector u. What is the length of the vector u? It's the distance from its start to the end. Let's represent the vector u as a combination of I and j. U equals. Let me call the coefficients u1 and u2. So u1 and u2 are numbers. They are called the components of the vector u. As always, we have vector I and j with the length 1. And what I did here, I represented the vector u as a sum of its horizontal component. So this horizontal vector is u1 times I, and the vertical component. The vertical vector is u2 times j. If I know u1 and u2, how to find the length of vector u? If I know u1 and u2, we need to use some theorem. What theorem do we remember? Look at this triangle. Do you see that this is a right triangle? Yes? Because the vertical and the horizontal components, these two vectors, they are perpendicular to each other because they are proportional to I and j they are perpendicular. This angle is 90 degrees, pi over 2 in radians. So let's use the Pythagoras theorem. It says that the length of the hypotenuse equals u1 squared plus u2 squared, the Pythagoras theorem. I emphasize that on the right, u1 is a number, u1 squared is a number, u2 is a number, u2 squared is a number. On the left, u1 is a vector, but u1 embraced by vertical bars is a number, the length. And the length squared is again the number. Please never have any equation in which you have a vector on one side but a number on the other side. A vector can never be equated to a number. A vector may only be equal to a vector, not a number. A number may only be equal to a number, not a vector. A number and a vector is totally separate, alien things to each other. So if I take the square root, I get the length, what I need, the length. Square root of u1 squared plus u2 squared. Now what happens when we add two vectors together and we know the components of the first vector and the second vector? Let's be specific. So far I've been theoretical. Let's be more specific. Let's add two vectors. Let's take u1, not one, just u, because one will stand for the components. U will be 3i minus 2j, and let's take another vector, v, to be minus 5i plus 7j. And what I want to do is to find u plus v. What do we do? Look, when you are after the sum or difference of two vectors, you apply the rules which are very similar to usual algebra. Look, 3i, first goes vector u, minus 2j, plus vector v. You may open a bracket if you wish. Then you write your vector v, minus 5i plus 7j, close bracket. Now you open your brackets and combine similar terms together. Combine all the terms with I together and combine all terms with j together. Where are the terms with I? This one and this one. you open the brackets using usual algebraic rule. You have 3i minus 5i, okay, plus or minus 2j. I may write differently. I write like this, minus 2j plus 7j equals. Let me continue here. How do we calculate 3i minus 5i? It's just minus 2i. 3 minus 5 is minus 2 times I. Or you may consider I as a common factor. You may write it as I times 3 minus 5. I is a common factor. What about these two? You may write like this, plus, open bracket, minus 2 plus 7, j. Am I right? Do you guys approve? Equals minus 2i plus 5j. That's it. Any questions? Quite simple, straightforward. Another exercise. Let's take u being j and v being minus I plus j. I want to find u minus v. U minus v. Let's do it together. For vector u, I component is missing. It's okay. The fewer components, the better. We should not be afraid of that. Well, we can think like this, that the second component is there, but the coefficient is 0 in front of I. We can look at this way. But look, we don't really need too much complication. Okay, let's first write vector u here. J. Then goes minus. This minus. Then goes vector v. Please put it in brackets. It's important. If you have minus in front, then what you have next, your vector v, must be in brackets. Vector v is minus I plus j. Is it correct? Now you open the brackets, using usual rules. J, this one. Then goes what? Tell me. Then goes vector I with plus or minus in front? Plus, yes, because minus and minus result in plus. Plus I. Then goes what? Using usual algebraic rules. Minus j. Correct? Minus j. Because minus and plus, they result in minus, the sign minus, j. What is that? Can we simplify this? Yeah, j cancels out. J minus j disappears. What's left is just I. You know what happens geometrically? Look at this picture. This is I. This is j. Where is vector u? Vector u is the same as j. It coincides with j. So j is our vector u. Where is vector v? Vector v is minus I plus j. Minus I goes to the left in opposite direction to I with the same length, 1. Vector j is still there. I minus I plus j is this vector, which I show in dashed line, because it's minus I plus j. Now when I subtract u minus v, I subtract from u, from this vector u, I subtract this vector v. How do we subtract u minus v? To find u minus v, I need to attach to the end of u the start of minus v. So from this point, I draw minus v. Minus v. The vector which is opposite to v in direction and having the same length. Then I connect the start of u and the end of minus v. And this vector is nothing else but I. Look, but you don't really rely on this geometric picture. This geometric picture is just an illustration. Just straightforwardly fulfill this algebraic operation and you will get the answer, I. That's all you need. Any questions, guys? Quite simple. Okay. See you next time.